For thousands of years, one of the most basic questions you could possibly ask, what makes things move and what makes them stop, had an answer that seemed completely obvious, but it was also completely wrong. So today, we're going to be detectives. We're going to crack this historical case wide open.
We've all been there, right? You're just standing on a bus, minding your own business, it hits the brakes, and suddenly you're lurching forward. Well, that little jolt you feel? That's a huge clue to a fundamental law of the universe, a secret that was hiding in plain sight for centuries. To get to the right answer, we first have to understand the wrong one. And believe me, it was an idea so powerful and so intuitive, it stuck around for over 2,000 years.
Now, we're not talking about some complicated scientific theory here. This was just common sense. It's what everyone, from the most brilliant ancient Greek thinkers to a kid playing in their backyard, knew was true, simply because it's what they saw happen every single day. The great thinker Aristotle was the one who really put this idea into words. He basically argued that for something to move, there has to be a constant cause. If an object is moving, something has to be pushing it or pulling it. The second you take that force away, the motion stops. Seems simple enough, right? And you can totally see why this idea was so convincing. I mean, experience is a pretty powerful teacher. Any kid knows you have to keep pushing your toy car to make it go. The second you let go, it grinds to a halt. Our daily lives seem to prove Aristotle right over and over again. But our world was hiding a little secret. So what was the big secret? What was everybody missing? It turns out Aristotle wasn't wrong about what he saw. He just couldn't see the invisible force that was always at play. The reason that toy car stops isn't because rest is its natural state. It stops because the floor is actively pushing back. That hidden culprit was friction, and it was fooling everybody. So, to find the true law of motion, someone had to imagine a world without that meddling friction. And that brings us to the first great detective on this case, Galileo. You see, Galileo's genius wasn't just in what he could observe, but in what he could imagine. He realized that to understand how motion really works, he had to perform an experiment in his mind. He had to mentally strip away the complicating factor of friction to see the pure underlying law of nature. Okay, so here's what he imagined. Picture a ball rolling down a ramp. It rolls up the other side, almost back to the height it started from. Simple enough. But then he thought, what if I make that second ramp less steep? Well, the ball still tries to get back to its starting height, but now it has to travel way farther to do it. So he took this idea to its logical extreme. What if the second ramp isn't a ramp at all? What if it's perfectly, endlessly flat? In this perfect, frictionless world he imagined, the ball would never, ever reach its original height. It would have no reason to slow down. It would just keep going at the same speed forever. And just like that, boom, a 2,000-year-old idea was completely shattered. The natural state of an object isn't just to be at rest. It turns out an object at rest and an object moving at a constant speed are kind of the same thing. They're both states where there's zero change. A force isn't needed to keep something moving. A force is only needed to change its motion. So Galileo cracked the case wide open. But it took another brilliant mind, Sir Isaac Newton, to take this amazing insight and carve it into a universal law, one that would become the absolute bedrock of physics. Newton formalized Galileo's idea into what we now call his first law of motion. It's a fancy way of saying that things just keep doing what they're already doing unless something messes with them. An object just sitting there is going to keep sitting there. An object that's moving is going to keep moving in the exact same way. It's that simple and that incredibly profound. And this resistance to change, this tendency for an object to just keep on keeping on, it has a name: inertia. It's a fundamental property of anything that has mass. In fact, the more mass something has, the more inertia it has, which means it's harder to get moving, and once it is moving, it's harder to stop. You can almost think of it as the universe's built-in laziness. But this isn't just some abstract law for planets and spaceships. No, you feel the effects of inertia every single day. So let's go right back to where we started. That bus. When that bus lurches forward, the bus moves your feet, but your body's inertia wants to stay put. That's why you feel thrown backward. And when it stops, your feet stop with the bus, but the rest of you wants to keep going forward. That's inertia.
A book on a table stays put because the forces on it, gravity pulling down, the table pushing up, are balanced out. And in space, where there's almost no friction, an astronaut really shows you how it works. One little push, and they'll just drift away at a constant speed, in a straight line, basically forever.
Okay, but what happens when the forces don't cancel out? To get to that, Newton had to introduce this really critical idea, momentum. The best way to think about it is as the quantity of motion something has. It's a mix of how much stuff is in it, that's its mass, and how fast that stuff is moving, its velocity. This is why a huge, slow-moving truck and a tiny, super-fast bullet can both have a massive amount of momentum. And that brings us to the real powerhouse of his laws, the second law. It says that a force is just a measure of how quickly an object's momentum changes. So if you want to change something's momentum, you've got to apply a force. Now, for most everyday objects where the mass doesn't change, this all boils down to that legendary equation F equals ma. Force causes acceleration. The bigger the force or the lighter the object, the more it's going to speed up or slow down. And this law is like a secret key for understanding so much around us. Why is a bullet so dangerous? Because its incredible speed gives it a ton of momentum, and when it hits something, that momentum changes in a split second, releasing a huge force. Why is a loaded truck so hard to stop? Its enormous mass gives it enormous momentum, and a cricket player pulling their hands back to catch a ball, they're just cleverly stretching out the time it takes for the ball's momentum to become zero, which makes the force on their hands a lot less painful. It's all about how quickly you change that momentum. And finally, we get to Newton's perfectly symmetrical third law, the one you've definitely heard before. To every action, there is always an equal and opposite reaction. But what does that really mean? I mean, if the forces are equal and opposite, why does anything move at all? Shouldn't they just cancel out? This is probably the biggest misconception about this law. People think these action-reaction forces cancel out, but they can't. And the reason is simple. They act on different objects. Think about a stone falling. The earth pulls on the stone, right? That's the action. But at the very same time, the stone is pulling on the earth with an equal and opposite force. That's the reaction. The forces are a perfect pair, but since one is acting on the stone and the other is acting on the whole planet Earth, there's no way they can cancel each other out. So there you have it. After a 2,000-year journey, we finally have our answers. We've gone from a world where motion was a complete mystery, guided only by our flawed intuition, to a beautiful, clockwork universe that runs on clear, predictable rules. And here it is, the foundation of classical mechanics, all wrapped up in 3 ideas. Number 1, inertia. Objects resist change. Number 2, the direct link between force, mass, and acceleration. And number 3, the fact that forces always come in pairs. With just these 3 laws, we can chart the path of a planet or predict exactly where a cannonball is going to land. These laws are incredibly powerful. I mean, they describe the world we live in and see every day with amazing accuracy. But what happens when we push things to the absolute limits? What happens when you get close to the speed of light, or you shrink down to the bizarre, tiny world of a single atom? Well, that's where Newton's beautiful, elegant rules start to bend a little. And that's where a whole new and even stranger story begins.